I would like to talk today about local operators after we talked about point operators a couple of weeks ago, and in the lecture of yesterday about binary, or day before yesterday, when we were talking about binary images, we also have seen local operators in terms, for example, of the erosion operator. And the idea is to not take into account a single intensity value in order to make the mapping from one image into a new image, but in take into account the neighborhood of that pixel. So at the beginning of the course, I showed kind of this slide over here. So the point operators do the mapping from one pixel in the original image to a single intensity value, a single pixel in the output image, not taking into account the intensity values, for example, of nearby pixel or any other pixel in the image. In contrast to that, global operators do the mapping taking into account all images that are available, that have been available. So that means every intensity value in the input image can influence an intensity value in the output image. And in between those two extremes, we have the local operators. Local operators, to map one pixel from one image to the second one, they actually take into account the local neighborhood of those images. And one of these examples for those local operators is the erosion operator that we were kind of briefly introducing on Tuesday, and also, for example, edge detection. If I want to identify edges in my image, that means changes, for example, from high intensity values to low intensity values, or the other way around, it's clear that I need to take into account the neighborhood of a pixel in order to decide if a pixel belongs to an edge or not, because it's a transition from high to low intensity values or from low to high intensity values over a local region that makes an edge for us. So the lecture today will focus on those local operators. And the reason why I'm moving from point operators to those local operators is, as I said before, for a couple of mappings that I may want to do, a single intensity value is not enough, and I need to consider the neighborhood of these pixels in order to extract relevant information. The other thing is also, if we have to deal with noise, maybe we want to smooth our image, that's something we cannot do with the point operators, and where we have to take into account neighborhood image or intensity measurements in order to perform that. So the topic of today are local operators, also sometimes called neighborhood operators, and we will look into a couple of the, different problems here. The first thing is, how can we actually reduce the noise in our intensity measurements, let's say, for example, over a homogeneous region. Then we look into Gaussian filters, which are also a way of smoothing an image, and we will look into gradients and actually show that with those local operators we can actually compute the gradients in the intensity images, and then finally briefly look into edge detection. So how can we use those filters to at least come up with a good proposal where edges are in those images. And the first thing, the most trivial, most simple operator of this type, taking into account a local neighborhood, is something which is called a box filter or moving average filter. What this filter does, it basically takes an intensity value, looks into the neighborhood of this intensity value, and computes the average of all the pixels in the neighborhood, and this gives me the resulting new pixel. So for example, if I'm interested in estimating the 1D case, so this kind of the 1D image, the output for a pixel I, for an intensity value at the location I. I take the original image at the location I and subtract some value, index value k. For example, k goes from -1 to 1. Then I would take into account the intensity values from I -1 to I plus 1. In this case, this capitalized K would be 3, so it would be 3 intensity values we would take into account, and I simply sum them up and divide by 3. So what it does, for every pixel, it computes the average from exactly the same pixel in the original image and the one to the left and the one to the right. This is what this first line does. So I'm simply moving over my image and computing the mean over the original index and the index plus 1 and -1, or -2, plus 2. What I can do in 1D, I can also, of course, do exactly in the same way in 2D. If I have a two-dimensional image, what's typically the case, and then I need to sum over those intensity values in x and in y direction, or in I and in j. That means simply have an area and take into account all those values in that area and simply compute, sum all of the intensity values up and divide by the number of intensity values for every pixel. That means for every pixel in the output image, I consider a local area, in this case a box, therefore this guy is also called box filter, a small box, and simply sum over all those values in the box, divide by the number of values, and I have my output. Okay, it's kind of clear what this box filter does. Okay, let's make a small example. So let's say we're living again in the 1D world, and these are my intensity measurements I have in my input image. So 100, 126, 110, 98, again 98. So these are the original intensity values that I have. Then I say, okay, I want to compute the box of the size of 3 pixels, means the pixel I'm considering and 1 to each side. And now I want to compute the output. So what we basically need to do for any index, say the one in the middle, we simply say there's 126 plus 110 plus 98 divided by 3. And this will be the output which goes here. If we can do that, it's done simply by simple computations, just taking into account blocks of 3, summing them up, dividing by the intensity value by 3, and mapping it as a new pixel value. So there are 2 elements, the one at the borders, which I put a question mark in there because we would actually need to take into account this intensity value over here where there is no value, or down here. We will look later in how we can actually handle those border values. For the moment, we assume that we are somewhere inside our image. Okay? So this is the simple box filter. Now we want to make the formulation a little bit more complicated, but not much more complicated, in order to embed this type of filter into a more general framework of filters. And what we're going to do is we use something which is called, say, a weighting function or a kernel function. This is this function W. And what I'm basically doing here, I'm kind of combining 2 functions. So this is my output. This is my input image. And I'm weighing every pixel in my input with some function W. So how does this look like for our simple box filter example? So for my simple box filter example, if we go back 1 step, every intensity value in my original image had the same weight. So I'm treating them all alike. Right? And simply in the end divide by k. So I can see that as weighing every of those intensity values by 1 divided by k, and then summing up those values. Okay, so in our case, k was k equal to 3. So I would simply define my function w of -1 equals 1 divided by k. So 1/3. W0 is also 1/3. And W1 is also 1/3. So simply, the function W has a constant value from the indexes -1 to 1 and is 0 anywhere else. Okay? Okay, this was just kind of the 1D example for our box filter. This is 2D, but it works exactly in the same way. So if we say, if this function W is simply a constant, then with this formulation, we can actually represent a box filter. What we will see later on, depending on which weighting function I can put in here, I can actually generate different types of filters. This is exactly what we are going to do more or less throughout the whole course today. So depending on how this function W looks like, I get different properties of my filters. If W takes the same values for every relevant input index, then I end up having a box filter. I can, for example, also vary those values and let's say make this value a little bit larger. Say 1 divided by 2, and then of course need to reduce the other a little bit. Let's say 1 divided by 4. That simply means the original intensity value has a higher weight when computing the weighted average. So this is twice as important as the two neighboring ones for this example over here. So this was the box filter, and this is a different filter. Where I simply put more weight on the actual value and less weight on the neighboring intensity values. So the reason why we come up with this formulation of using this kernel function W is by specifying this kernel, I can actually have different properties that my resulting filter will have. We can actually show that we can use those filters in the end also, for example, to compute the gradient of the intensity values by just putting some smart numbers in there. So we're looking today into these linear filtering operators, which basically combine those intensity values with a linear function, and the coefficients of this function are simply specified by this function W, or the weight function, within a neighborhood. Typically it's a small neighborhood, but in theory no one prevents me of making this filter W very, very large and actually smoothing over my whole image. So if W is large enough, I can actually see this also as a global operator because it can take into account all the intensity values in my original image. But in practice, one typically uses a small neighborhood, small size of this kernel function. So again, I'm summing over all relevant indices. Typically, this is centered around 0. Take this kernel function into account and my original image. Okay, so and I told that this is actually a linear filter, to be called linear filter, a filter which has these properties. So the transformation L in here, which maps my original input to my output, is one which has the following two properties. The first property says I can actually combine two images, F1 and F2, just adding those values, adding up their values, maybe with an additional weight, and I compute the operator. I actually obtain the same result as I would execute the operator on the original image and weighing them. So this can be seen as L of F1, and this is L of F2, which gives me G1 and G2. So I can actually separate this process of either transforming every image individually and then summing them up, or I can first sum up the images and then perform my operator. I get the same result. And the second one is a property down here, which basically means it doesn't matter at which location the operator is applied. So the operation is independent of the location of that filter. So it doesn't matter where I actually execute, that the operations are the same. It's not that in the left part of the image, I use a different transformation compared to the right part of the image. Of course, if my input are different intensity values at different locations, I will get different output. But if I use, so the transformation itself stays the same over the overall image. Okay? So given that we defined our operations using these kernel function, so exactly in that form over here, kind of just swap those two elements compared to before, there's actually a mathematical concept which is called convolution, or in German Faltung, which we are actually executing here. So we are convolving two functions, f and w, and the output is the convolution of those two functions. And this is typically written in this way, f star w. And it means exactly this operation for the discrete case. If you go to the continuous case, that would turn into an integral, but the rest would basically stay the same. So this, if we write something like this, we exactly mean what's written over here. And we can even specify this as these indices running from -infinity to infinity. And simply the kernel function gets 0 if we are far away, or far away than my local neighborhood. So we can actually see, yeah.
Where's the difference of this to the linear filter?
No, this is a linear filter.
Ah, okay.
So this, what's written in here is just the idea of using this convolution. And what we are doing here is this function w simply gives me coefficients, exactly those here, and I'm computing a linear combination of the intensity values according to this function W. And therefore, we basically have a sum of individual intensity values, all with their own weight, and therefore we're ending up having a linear operator. So the important thing in here is that this concept is actually called a convolution. We will look into the mathematical properties of a convolution in a second, and we can actually write it in this way. Okay, so this is basically just the definition of what we are doing. So is there any questions so far about that? So just to sum that up, what have we done so far? We presented a simple example on how a local operator looks like or can look like with the box filter, which is probably the most simple one we can imagine, which just takes neighboring pixels into account and computes the mean of the intensity values. So we said, okay, we have this kind of simple equation we can write down. Let's make this equation slightly more general, slightly more complicated by adding this weight function W, or this kernel function, what it's typically called. And then say, we can simply see this as the product of those two functions by changing those indices, messing around with the indices a little bit. So we sum over typically a local area. So in practice, this is a local area over here. And using this function W as coefficients for computing the weighted mean of the intensity values. So I'm going from those first intensity values, so the input intensity values to the output intensity values, and this W basically specifies me the weight of the individual intensity values. So which influence has a neighboring pixel in my input image to the output. So because if I, for example, for this want to compute the output value for an index 0, this function tells me what the influence of a neighboring pixel on my intensity value at the location 0 in this example, or at the location I actually want to compute it. So these are the weights, kind of, you can see that as weights telling me what's the influence of the neighboring pixels onto the output pixel. Okay. Now we're going to want to illustrate that we can actually see this box filter as one of those convolutions which I kind of just sketched over here. So we can first say, for the box filter, we can say J equals our function f convolved with this magic thing over here. And the R is here stands for the box filter, and there's kind of two numbers attached to it. The first one, the guy in brackets over here, is simply the dimensionality of my filter. So the 2 means I have a 2D filter. So I have an X and an Y, or an I and an J. And the second one number down here tells me something about the size of this kernel, also called the neighborhood. So if I have 3 values in here for the box filter, that means I have just 1, 2, 3 elements. And if it's 2-dimensional, I have 1, 2, 3 elements in the first dimension and 1, 2, 3 elements also in the second dimension. So this is my kernel function for the 2D case, and this is my kernel function for the 1D case for the box filter. There are some values which are underlined over here, those two guys. And what this means, this is the element with the index 0. So W of 0 returns me this value over here. Okay? Just to define where the 0 index is in those functions. Now we can take one of those values over here. Let's do that for the simple 1D case. Then we can say, okay, this is a relation, kind of the 1D convolution. And we now simply explicitly write that down. So we say k goes from -1 to 1. So if you want to compute the intensity value of the output image at a position I, so g of I, that's what we want to compute. We compute the sum, k going from -1 to +1, -1, 0, +1. We have to evaluate this expression. So the first expression, this block over here, k equals -1. So this is w of -1, f of I minus -1, which equals f plus 1, plus, and we have the index k equals 0, w0, fi minus 0, and the corresponding one for the index k equals 1. Now we said this is our box filter. Takes values 1 divided by 3, 1 divided by 3, 1 divided by 3. So I can put that in there. 1 divided by 3, 1 divided by 3, 1 divided by 3 of my individual values. That means we set W to this value. This is kind of my box definition of the box filter. And then I can kind of introduce this extra bracket and move 1 divided by 3 out. And then I had the original definition of my box filter, which was the sum over of 1 divided by k, capital K, and then the sum over those values over here. So we've kind of simply shown here as an example that the box filter, which computes the average, can be expressed as a convolution. And now we can actually do one small thing in order to simplify the computation a little bit. Let's say I have an input image, again 1D case, whatever, like this, 3, 4, 5, 2, 1, 5, some values. And I'm now, so this is F, and I want to compute this intensity value for G of I. So this is my location. This is my location I at the moment. I can say, okay, I have my kernel, which has a neighborhood of 3. So I can actually draw that guy over here on top of it. This is my function W. And now I need to put the corresponding values for W in there. And I need to take those values, compute the sum, and this sum then gives me the output value G of I. And if I do that, I need a little bit take care about the sign. So this corresponds to W of 1, W of 0, W of minus 1. So kind of the W is, if I kind of illustrate it like this, is swapped. So it doesn't matter if I swap the W or I swap the F. What you then need to do, you just multiply those two values, we multiply those two values, we multiply those two values, we sum them up, and this gives me the corresponding intensity value. So in our case, this would be all 1 divided by 3, so it's, this equals to 4 divided by 3, this is 5 divided by 3, this is 2 divided by 3, and then I kind of sum up those values, so it's 11 divided by 3 will be the output value here. I can see this kind of having this kernel which simply slides over the image. At every position we stop, compute the sum, move it one step further, compute the sum, and so on. Okay, is this kind of clear how that works? Okay. Yeah.
But you always apply this filter or this box to the original value. So
yes.
You do not apply them to the already changed values.
Yes, exactly. So I compute them here, put the result in here. This function f does not change by this operation. So I can't do that in place, so to say. So if I'm in my computer, I just have one image allocated here. I cannot simply apply that and store the result in the same image, because this will actually screw up the computations. Why? Need to take care that I copy the corresponding values. I can do that in place, but not straightforward. I need to kind of store the original values. So and this is kind of then the output image. Okay, let's look to an example how that looks like. Let's say this is my input intensities. So for every location here, I have an input value over here, and this is the convolution of the original function f and the simple box filter in 1D with a neighborhood of 3, which basically says for this value we simply take the average of those 3 guys. For this one we take the average of those 3 guys, and for this value we take the average of these 3 guys. And this gives me these intensity values over here, and this is my signal. You can see about the signal is smoother than this original signal. Right? Because of less variation here in those values, because I simply computed averages. Can take that one step further. So this was the result This was shown on the right in the previous slide, and simply added here a convolution with a box filter with a neighborhood of 5, so a larger one. Then you can actually see that those results actually get even smoother. You may think, why is this value different? Why is this one increased? The reason for this one in this example, for the missing value, for the first one that I computed, I simply took the value on the other side. It's one of those things that you can do. Therefore, this guy moved up a little bit, but the remaining results are much smoother. And you can see that this, in the original image here, we had a large step over here, more like a step function, and here it's turns into a rather smooth function. So what the operation does, it actually smoothes the output, on German Glättung. Okay, so we have, again, the box kernel. So this was the box kernel in the 2D case. Again, the underlying guy simply indicates this is the index 0, which corresponds to 0. And one of the things that the kernels we showed so far, the sum over all those values is 1. So this factor here. So these are 9 times 1 divided by 1. So this is 1. And I need to make sure if I want to kind of just do a smoothing without changing the mean of the original intensity values, so the mean over the overall image, that the sum over all elements actually ends up being 1. If I wouldn't divide by 9 in here, I would simply increase the mean of my function, because I would simply, every pixel would be the sum of 9 other intensity values without dividing by 9, so the mean would be 9 times larger. Okay? That's the reason why I always have this scaling factor here in front of those kernel functions. Only if the kernel function, the sum over all elements of the kernel function is 1, then I don't change the mean. Otherwise, I would change the mean. So there are other important kernels where this is not the case, where the sum doesn't end up in 1, for example, the sum being 0, but then we have different properties. Okay?
Sorry.
Yes?
If you do this,
yeah.
Then you're not working with integers anymore, right?
Of course, I need to do rounding operations in this case, okay. Yes. So basically...
You get additional changes just by rounding.
Yeah, so that, yes, there are two possibilities I can do. The first thing is I can simply do a rounding operation if I still work in the space of integer values, so if the intensity values are integers. What I sometimes do if I have multiple of those operations, I simply change to continuous values and then perform this operation. But in general, you're right. So the output here may be not an integer value. In this case, I either need to round or I need to choose a data structure which allows me to take floating point numbers into account. Okay, any further question about that so far? Okay, so the next thing we want to look into is actually the changes of the standard deviation of the variance from the input image to the output image if I apply such a filter. So I said I can use those filters to reduce the noise. So the next question then, how does that actually changes? So what we can do, we actually have a general equation for how this convolution changes the variance from the input signal to the output signal. And this is this kind of general equation for the discrete case down here. So the noise in the output image, specified here by the variance, is the sum over the individual coefficients or squared coefficients of my kernel function, about the same neighborhood, and then the overall multiplied with the original variance. So that means for the box filter, what we have in here is, let's say we do that for the 1D case, and we have a neighborhood of m, that means m different values. So then the variance of the output, so G, equals the sum over m elements of 1 divided by m squared. So this 1 divided by m was the corresponding factor in my kernel. and I need to square them because here's a square. So if I sum exactly over m values, this is m divided by m squared equals 1 divided by m. Okay, of course, I forgot the sigma n. I forgot the other factor. So that means, the result of that, for the variance, we have a factor of 1 divided by m. That means for the standard deviation, we have the square root of m. So this holds for the 1D case. For the 2D case, I don't only have m values I have to sum over, I have m square values. So for the 2D case, we have this sum over mm, so m in I and m in j, by 1 divided by m squared. So this gives me m squared divided by m squared. No. Okay, what went wrong? Oh, found the mistake. The mistake was not that this is m squared. This is m squared squared, so m to the power of 4. Because it's kind of every value of my grid is 1 divided by m squared because I've added m and m. So it's 1, 1, 1, everything in 1, and I divide 1 divided by m squared if m is the number of elements here and the number of elements here. So this is m to the power of 4. So this is 1 divided by m squared. Compute the square root of that. Exactly have my factor 1 divided by m. That means the box filter reduces the variance of the intensity values in the 2D case, so for what we have typically if we work with images, by a factor 1 divided by m, where m is the size or the neighborhood of that filter. Okay? So we may argue now, if we want to eliminate, for example, some of the outliers that we have, we may not take into account computing the mean using the box filter, but we can actually do the same with the median. And then simply compute the median to be more robust under outliers. It works exactly the same as the box filter, except that I don't compute the mean over the box filter, but simply the median. The thing is that it's not a linear filtering operation then anymore. It's one thing we need to take into account. But we are robust against outliers in the intensity values. So if we have some extreme outliers in our intensity measurements for individual pixels, we can actually eliminate them quite well. I don't go more into the details, but because this is something of the homework assignments that you will actually have to do, and then actually explore the median filter. Something we haven't talked about yet, I said in the beginning, we'll see how we handle that, is actually how to deal, what are we going to do at the borders? So if one of those indices for which I have a weighing coefficient unequal to 0, but I'm actually outside my image. And of course, the larger this, the size of this kernel gets, or the neighborhood gets, the closer I come to the border, the further I'm away to the border, I still already have that problem. Because the kernel needs to fit perfectly into the image in order to compute the right values. If I'm going toward the borders, I'm actually need to simply specify what I can do. One of the things I can do is simply add a constant value. So I assume every image outside, every pixel outside is a constant value. One of the things I could, for example, do is say I use the mean of all intensity values for the outside border. At least I don't change the mean with my filter operation if this is a box filter. Maybe something I could continue. Other things, what we can actually do is what's called a cyclic wrap. If I'm kind of at the border of the image in one line over here, I simply say, okay, the missing intensity value is simply the one over here. Something which can frequently be done. The other thing is kind of clamping, simply taking the missing pixel and repeating this towards infinity. Or what often gives kind of nice visual impressions if I just kind of have a mirror. I just take the image and mirror the image to the other side. So kind of as a small example, so if this is kind of a gray value I want to compute the convolution for, I can either fill that up as constant values. So here it was not the mean, here was simply 0. So I have kind of this, simply expand my image with zeros and simply compute the filtering operation on this new expanded image. Or I do the cyclic wrap, so simply whatever is here, I copy the intensity value from here, and whatever is here is a copy of the intensity value from here. Or I clump those values, I basically expand those values, or I do the mirroring. Simply mirror the whole image within this small frame. These are kind of 4 different strategies I can do. And basically depends on what I actually want to compute to decide if this is something which makes sense for me or doesn't make sense. So it depends on the filter, which properties I want to have. If I want to, for example, make sure the mean of the intensity values do not change, I would go for the constant strategy, but don't set it to 0, set it to the current mean. Because if I smooth over the mean, I don't change the overall mean. If I add additional values here, which are, for example, higher or lower, like 0 here, I will change the mean of the overall image. So basically it depends on what properties I want to have for my output image. What's the relation between the output image and the input image? Should those images have the same mean in terms of intensity values? Or should they have any other properties? So for example, if I have strongly varying intensity values at those borders, a constant value may not be a good choice. In this case, kind of the mirroring operation, as we can see it here, may give a nicer visual impression. The question is always, what do I want to do with my with the output image? It simply depends on that. Okay, what we discussed so far was basically the box filter, the idea that the filters can be expressed through convolutions, and we looked into the case how does the variance of the intensity values changes, and what are we going to do at the borders. So kind of most of the things are actually done for the box filter. Next thing we look into is the second very important filtering, which is the binomial filter, or in English typically called the Gaussian filter. So Gaussian filter is a more frequently used term, at least in English. In German, that's different. There's the binomial filter. So also this filter performs the smoothing. So it smoothes the input image for the output image, and it got the name from the kernel function that it uses. So it's exactly the same technique that we use the convolution in order to compute the new intensity values, but instead of using, for example, for the box filter, a constant function, it simply uses the Gaussian distribution. So W is a normal distribution. Typically, or what we typically have, we have a small set of indices or pixel values. We go to the left and to the right. So what we actually use, we use the coefficients of a binomial distribution, which can be seen as an approximation of the Gaussian distribution. And this is exactly for the case of having 3 elements. This is the corresponding Gaussian filter, or binomial filter B. So the elements in the middle have a higher weight than those towards the border of the kernel function. So you can see this as kind of the Gaussian distribution with the mean here in the middle and decaying towards the border of the weighing function. This is here the example. So for the 1D case and for both 1D cases, 2D cases, taking account different neighborhoods. Here now the neighborhoods are differently defined. They're basically defined, so this is for the neighborhood 2, so they're not 2 values, but the number depends on how I actually generate those kernel values. So here, this was exactly the example I had down here. And this one is the next larger step. And actually, I can obtain those elements using Pascal's triangle. So we'll go through the Pascal's triangle, and that's also where the number comes from the row from the Pascal's triangle to obtain those values over here. So what I can now do, I can again take my original input image function and can smooth it with the Gaussian kernel with different neighborhoods, so different sizes. And again, the larger I make these values over here, the smoother those functions get. But the operations I execute are exactly the same as I did for the box filter, except that not all intensity values get the same weight. They simply get now different weights. So the original intensity value has a higher weight as those of the neighbors. And this is a function that you actually probably used already, at least if you do something with work with images or with standard Photoshop. Let's say you have here part of the logo of the University of Bonn, which is your input image, and you basically select in your image manipulation program blur, make image more blurry, or Gaussian blur. It's exactly what executes such a filter. In this case, was a filter with a neighborhood of 30, and then you get this blurred view of the original input image. Okay? So is it clear to everyone how we actually use those filters? We use them exactly in the same way as the box filters. The only difference is that the individual values for this function w are now different. We can also look how the variance changes, so exactly these computations we had down here. Now the math gets slightly more complicated because I don't have 1 divided by m in here. I have, for example, for this case over here, I have 1 divided by 2 squared plus 2 times 1 divided by 4 squared. And this is a sum, and this gives me a different smoothing. And actually, the smoothing in the 1D and the 2D case can actually be seen over here without deriving how we actually end up with that. But what we can see is just from the functions over here that both filters actually smooth the performance smoothing. So the noise reduces, but the box filter has actually a higher degree of smoothing. We can just compare those values. We can do that by, if you kind of want to extrapolate from the exact neighborhood that we are actually using, we can say we have an image and we want to have a certain degree of smoothing. So going the other way around, not saying here's my input image, here's the kernel with a certain size, smooth it. If you say we want to have a certain degree of smoothing in my output image, which filter should I actually use? It's kind of the more realistic choice that we may need to do. And we can compute the degree of smoothing at the ratio between both standard deviations, which is actually very similar to what I did here. This would be r squared. And if you do that, we obtain for the degree of smoothing for the box filter is actually 1 divided by r. So this is all for the 2D case. It was exactly what we had. What we had here. So if we have a direct relation between the neighborhood and the degree of smoothing that we actually obtain, that is actually here. And for the box filter, for the Gaussian filter in the 2D case, we actually have this relation over here. So that means the box filter actually smoothes more. We have a larger degree of smoothing in here because those values are larger than those values. So if I, for example, want to have a degree of smoothing of 1 divided by 5, so I need to put 0.2 in here, I need to choose a kernel width of 5 if I go for the box filter, or approximatively a kernel width of 8 for the Gaussian filter. So I need to select a larger filter if I want to, for the Gaussian filtering, a larger kernel for the Gaussian filter if I want to obtain the same degree of smoothing for the Gaussian filter as for the box filter. Okay, we'll stop here, make a 5-minute break, and then we are continuing with convolutions. We want to look into the mathematical concept of convolution, or in German Faltung, in order to better understand the properties of the smoothing operations that we actually perform. So what we have shown is that we can use or express the box filter as well as the Gaussian filter as the execution of a convolution to our function. So we have our output image, which is given by the input function convolved with our kernel function. The idea is now to look into the properties of the convolution to understand a little better what's going on. So just for the discrete case, the convolution is defined the output as a convolution of two functions a and b, exactly in the same way as we specified it. The only difference here, this factor k goes from minus infinity to plus infinity, and the kind of trick is simply that the kernel function is 0 outside our neighborhood. And then we actually obtain the same result. We can do the same in 1D and the same thing actually in 2D. So that's just the definition. The next thing we want to actually show is that we can show that A convolved with B and B convolved with A is actually the same thing. And we can do that by saying, okay, we simply take the definition of A convolved with B, which is exactly this one over here. And now we simply replace indices. So we're introducing a new indice J, which equals I minus K. So this one will be J. Okay? Replace this one with J. If this is the case, we can also say that K equals I minus J by just taking this equation, minus K minus J, and then K equals I minus J, and then we replace the K's in our equation by I minus J. It's just kind of simply introducing a new character, a new variable, and then doing two replacements, cleverly replace, pattern matching and replacing in the original function. Then we end up with this function down here. We are now equivalent to the equation up here. The only difference is now that our variable is called K and it's now called J instead of K, but it's used exactly in the same way. The only difference is now that the function B has the raw variable, and B has the original queried variable minus the variable from my loop. So we can conclude from that A convolved with B is the same as B convolved with A. So it doesn't matter if you write F convolved with W or W convolved with F is exactly the same result. Similar to that, we have most of the typical properties we know. For example, the associative properties. So if A convolved with B convolved with C, it doesn't matter if I first convolve A and B and then convolve the result with C, or if I first convolve B and C and convolve the output with A. It will be exactly the same result. The distributive property also holds, as you all know that, similar to the German saying Punktrechnung vor Strichrechnung. Actually works exactly the same way in here, and we can use a distributive property to multiply that out. So I say if A convolved with C and B convolved with C, and then add them up. So not C plus B convolved. This wouldn't work. But A convolved with C and B convolved with C, and the result is simply end up this. And what I can also do, I can use a scalar multiplication, and it doesn't mean it doesn't make any difference if I convolve A and B and multiply the result with a scalar, or if I use a scalar to multiply the first function and convolve it with a second function, or the other way around. So these are kind of some of the properties that you will need to know in order to deal with those convolutions. There's also one element. If I convolve a general function f with one specific kernel, is there any kernel which does not change my original function? It's a kind of a neutral element of the convolution. So if I have an arbitrary function f, I want to convolve it with a special kernel so that the output will stay f. So how does this guy look like? So W0 equals 1, and so yeah, and it's 0 for W whatever I not equal to 0. So if I do this, it's called the unit impulse. This value is 1, all other values are 0, or in the 2D case, and if we convolve A in the unit impulse, we actually obtain A. What happens now if I kind of keep the unit impulse, but I change the location of the 1. Say, move it in this direction, 1 up, or here, 1 to the right. What happens then? Yeah?
Kind of a shift.
Yeah, it's a translation or it's a shift. So basically, you can shift all the image by 1 pixel, for example, by just moving the 1 up. And if I move the 1 up or down, it now makes a difference in which direction I shift. And make sure you move to the right-hand side, because if you have kind of this drawing I had here before the last hour, where the W is written over the F, you need to make sure you swap the W in order to get the correct values. So as soon as the thing is not symmetric anymore, we get a different results. All the examples of the kernel so far have been symmetric ones, but as soon as I shift the unit impulse in one direction, it's not symmetric anymore. And what I then can actually do is I can actually realize a shift. So if I want to shift my function by x and y, I can do that based on the unit impulse. It's just exactly what we have said before. So the question is, how does the function actually, how can actually by hand compute a convolution? And the convolution is actually very similar to the mathematical multiplication that you learned at school. So the only difference between is that the multiplication uses a carry operation. So what's also called in Deutsch der Übertrag, wenn ich über die Zehner rüberspringe. And I don't have that here for the convolution. But this is exactly like doing your multiplications in school. So in this example over here, if I want to convolve the kernel 1, 2, 1 with 1, 2, 1, kind of multiply this one with this guy, the second one with the individual elements and write them down here. Same one here, and then actually sum up those values. The only thing which is missing is kind of if this guy would be larger than 10, I would have my impulse larger than 10 here and wouldn't add that up to the next element. So that's kind of the missing carry operation of the flag. Can do that in this example over here. If I convolve those two guys, first thing I kind of move the scalar out. This is then 1 divided by 16. I convolve those two elements, which I exactly do with this operation here, and then this is the resulting kernel that I get. So this is a way how you can actually do that very similarly by hand. On the other hand, yeah. So this is just kind of an easy way for doing the convolution by hand. Under certain properties, we can even undo the convolution. If we have the convolved output and we want to go back to our original image, depending on the properties of the kernel, we can actually do that. And there's a question if we can actually do something that's called deconvolution. So if the inverse of the function a exists, so a minus 1 exists, and there's no element where a takes a value of 0, because if a takes a value of 0, if w has a value of 0, for example, it simply eliminates a certain intensity value, and if it's multiplied with 0, actually you can't recover that by using the inverse kernel. So if I only have the output of a convolution with b, and I take the output and convolve it with the inverse of a, I actually obtain my original input image b. So under the assumption that this kernel is invertible, so the inverse of the function actually exists, which then I can actually go back and undo a convolution, do a deconvolution, kind of remove the effect of a convolution. The next quite important property is something that's called separability of a kernel. So if you have multidimensional kernels like here in the 2D case, or in higher, you can even do that in theory in higher dimensions, but here the maximum dimension we have here is 2 because we're working with images. And if I can actually split up a kernel into two 1D kernels, which I can basically do by overlaying them and then shifting them to all possible positions. In this way I can actually obtain the output result. That means that doing a convolution in 2D with this kernel can actually be split up in doing one convolution in the dimension of I, and one followed by a convolution in the j dimension. And this is kind of a rather important property, because This allows me to do several of those computations very fast. Of course, this is not possible if this guy is not symmetric. So let's say I put a 100 in here. Then I can't generate this kernel with two individual 1D kernels. And but if this is the case, if the kernel is separable, then I don't need to do a convolution in 2D. I can actually convolve my image in 1D. And this is important. Instead of computing one convolution in 2D, doing two convolutions in 1D, because doing the convolution in the lower dimensional spaces is computationally more efficient. So this one here, this operation requires a quadratic number of operations that I need to do. And it's quadratic in the size of in the neighborhood of the kernel. Of course, it also depends how large f is, but if, let's say, f is constant, so the image size doesn't change, then the number of operations I need to do depends only on the size of my kernel function. So if I have n elements in the x direction and n elements in the y direction, then I have n times n operations I need to do for every pixel. So for every pixel of f, I need to execute n square operations, right? Because I need to touch every single element of this kernel over here. So this has n square elements because it's in 2D. So I have n elements here and n elements here. So this is, I have n square individual elements. And for every pixel of the original image, I need to compute these n square elements. So this is an operation which is quadratic in the size, in the number of elements that the kernel contains. Whereas this operation, where I first do a convolution here and then do a convolution here, this requires only n elements because this kernel contains only n elements. And this output also contains only n elements. And I do them one after the other. So it's 1 times n plus 1 times n is 2 times m. So this is a linear complexity in the size of the kernel, and this is a quadratic complexity in the size of the kernel. So if those kernels 2D kernels are separable into two 1D kernels, it's always more efficient to execute it in this way. So convolving the individual dimensions separately rather than doing the convolution with a 2D kernel. Simply more efficient to do it that way because I have a linear number of operations in the number of elements in the kernel compared to a quadratic number of elements, computations I need to execute. Okay, this is kind of clear why this is a difference. So there's a pretty important property of those kernels, of the convolution in general. So it's clear to everyone why this takes n square operation and this takes n or multiples of n operations. So for every pixel of f, I need to do n square operations in here because this kernel has n by n elements, so n square elements. This kernel has only n elements. I need to touch every pixel just n times. In the output, every pixel again need to touch n times. So it's n plus n and not n times n. And this makes the substantially different computational complexity. So it's a different complexity class that those two operations have. Okay, so if we consider the smoothing filters that we have, like the box filter or the Gaussian filter, they all have the property that's a sum over the of the individual elements of my kernel function is 1. Said that before, if this is 1, then the mean doesn't change. It smoothes my image, computing a weighted sum of intensity values from the original input image, but it does not change the mean here. What I can also do is, I can actually, if I want to do one operation with a large kernel, I can typically express this as multiple convolutions with small kernels. So if I have one kernel And this kernel can be, so this is kind of the large kernel over here. And so I'm not sure if this index is right. So this is actually wrong. So this should be a 1, not an n. I'm sorry for that. So that's a mistake. So this is a convolution of the same kernel of the same neighborhood. So if I have n elements in here with a kernel size of 1, then having one kernel with size n is equivalent to executing n times the box kernel in 1D. So if I, so binomial, this one, but it doesn't make a difference in here. So if we have a binomial filter over here, for n equals 2, we can actually get the same result if we twice execute the one of 1. Or if we want to have n b4, we can twice execute b2, or 4 times b1. So if you go back where we had both kernels actually shown exactly over here, so this was a b4 kernel, and this is, so this is a b4 kernel. This is exactly the same result as doing twice a convolution with a b2 kernel. Okay. And then there's kind of one important operation that we can do, and the trick is that what I want to show is that we actually can express this with, again, also convolution. So what we have in here is something which is called an integral image. An integral image simply computes the sum of all intensity values for all elements which are in the upper, so the part of my image. So this is an integral image of an input image f. What that means, the value which is in here corresponds to the sum of the intensity values of f, of the fij intensity values. This element is stored in here, in ifj. So it's simply the sum of all intensity values in the upper left part of the image. So this one stays the same because there are no elements in here. This element here is the sum of, this element in the intensity in the integral image is the sum of the intensity values of those two pixels in the original image, and so on and so forth. So in the integral image, which is here called S, Vs, of ij is simply the sum of all elements from 1 to ij of my input image. And I can actually use the box filter to actually compute those values if I don't do the normalization. So if I don't divide with 1 divided by n squared for the box filter, so if if I ignore the factor, then I can actually use this to compute this integral image in this way. And integral images are quite frequently used. So here's again an example for an original image and the corresponding integral image. So 3 and 3 is the same value. This value is 5 because 3 plus 2 is 5. This 11 corresponds to the sum of those values over here. So 5 plus 2 plus 1 plus 3 is 11. So we have an 11 here. What I now want to do, if I want to compute the sum of the intensity values of some inner part of the image, like the green area over here, if I'm only interested in computing the sum of this block over here, I can actually do that in the integral image by 4 operations always. And these are those elements which are labeled over here. So because what I need to do is the sum of all elements shown in the green area is this element in the integral image. So this is the 48 over here, minus all those elements over here, which is the value in 40 which is stored here. So it subtracts all those values. And minus all those values over here. And the sum is here written with 13. The only problem is that this block over here I've now subtracted twice. So I need to add that again. So by computing this element plus this element minus this element minus this element, I actually obtain the sum of elements here in this green area. As you can see here by this computation. So the sum is 24. 1 plus 5 plus 3 gives me 9. 2 plus 3 plus 1 gives me 6. And 5 plus 1 plus 3 gives me 9, gives in sum 24. So the important thing is, once I have computed this integral image, I can compute the sum of intensity value of arbitrary boxes in my image in constant time by just 4 operations. I just have to execute those 4 operations, and I can compute the sum of those intensity values. And therefore, this is a quite frequently, integral images are quite frequently used technique if I need to estimate how many intensity values or how many values are stored in certain regions of an image. Because it can very efficiently express this, do all the computations in the integral image. And then computing all those sums or differences can actually be done in constant time. No matter how large the image is, once I have the integral image, I don't care if this image is whatever, 1 billion by 1 billion pixels. As long as I have access to the integral image, I can compute the sum of the intensity values fast. Any questions so far? So what we discussed now in the second part of the course is the properties of the convolution in general, and also seen that we can deconvolute under certain assumptions an image. And we have right now, say at least I told you that we can actually use the box filter if we ignore the normalization constant in front of it in order to compute integral images. And integral images allow us to do constant time operations for computing sums of certain areas in my image. Of course, if kind of this green area, let's say, has a hole in there, I need to compute the sum of the green area and then subtract the hole again. So depending how complex this shape gets, I may need more than 4 operations, but I typically can deal with just a very small number of operations that I need to handle. So all the filters that we've seen so far have been smoothing filters, or Glättungsfilter, basically smooth my image. Now I want to move actually to a different type of filters, which are so-called gradient filters. And what I want to compute is the derivative of the function over intensity values. So I can interpret my image as a 2D function of intensity values. An x and y coordinate, and they are mapped to an intensity value. And what I now want to do is actually want to compute the gradient of those images, of those intensity functions. As we can see, we can actually use them to derive certain properties of an image later on. So let's go back to the 1D world to simplify our life. So consider that this was the function of intensity values in the continuous case. And what we have if we operate on an image, we just have a discretization of these. So these could be intensity values. So it's slightly getting brighter, and then getting slightly darker, as long as I move to this direction. If I want to compute the gradient of this function, of the red function, what I can do is I can simply pick 2 neighboring points and fit a line through those points. And this is simply, so the slope of this line I'm interested in is simply the difference in the y values, so in the intensity values, divided by the difference in x, so kind of the pixel differences, which would be this one over here. So by dividing this one to this one, I actually get the slope, and this way the first derivative of this function. Of course, it is only an approximation because we have this fixed distance of my pixels. But let's see if my resolution of the image is reasonably high compared to the variation of the intensity function, I can see that as a pretty good approximation of my intensity values. Of course, if I have an intensity function which changes between very bright and dark values very often, and the pixel size is very large, this won't give any good results, not at all. But if the change, as in this example, is rather small compared to the distance of the individual pixels, that actually works quite well. Okay, so we're going to compute this value now. So we can say the gradient is the difference in f and the difference in x in my image. And these are two neighboring pixels. This is simply the intensity value at the location I plus 1 minus the intensity at the location I minus 1, so two neighboring pixels. And I have to divide this by this, the distance of those two pixels on my kind of grid structure on my sensor chip. Or even if I abstract from the sensor chip, I simply express this in pixels. Okay? So what I now can do is I can take this delta f. So delta f of I is so if I just look into the difference of the intensity values at the location I simply have this equation by simply ignoring the delta x down here. Okay? So once I have that, say, okay, I have simply two intensity values that I need to subtract. Right? So what's written here is for one location, I just subtract two intensity values. Can I express this with a kernel function and use this as a convolution? How can I subtract one pixel value from its neighboring pixel value by means of a convolution? So I have my image f, and I have this value is whatever, 2, 3, 1. And for every of those elements, I want to say, take, for example, whatever, this value over here and subtract it by this value over here. So this would be 3 minus 2, so 1. And this value would be 3 minus 2, would be minus 2. That's the output that I want to get. This is my g and this is my f. And the kernel, which allows me to do that, is simply 1 and minus 1. Right? If I take this kernel over here, okay. So this is the 0 element. So it's not symmetric now. This is one neighbor because I just have two function elements which are involved in here. So let's simply define this as delta, and then I can say delta convolved with f actually gives me g, which is the first derivative of f. Just by defining this delta to be this operation and using a convolution with that. That's exactly what I do. We can simply define a vector delta, which looks like this, so that the difference of two neighboring pixels can be expressed as a convolution of this delta and f. It doesn't matter if it's delta convolved with f or f convolved with delta. And this is exactly this according to the definition of my convolution. So is this clear? So the only thing I've done in here is I want to compute the difference of two neighboring pixels. And I do that by using a convolution operator. Okay? Okay, now we can also do, let's say, maybe I don't want to take just this pixel. Let's say I want to smooth and take two of those pixels here, one to the left and one to the right, to be less sensitive to changes in my intensity values. Then I simply say, okay, we can also approximate my first derivative by delta f divided by delta x, where the intensity values are 2 pixels apart. So for a location, I take one to the left and one to the right. So this is f plus 1 minus f minus 1, and now the difference in x is here 2 times delta x, so the width of a pixel. Okay, I can do a copy paste with the slides I had before. If I use this, I can say, okay, delta f is then those values divided by 2. Of course, we have this additional 2 over here. So in this case, I can define a different weight function or kernel function, which looks like this, and can rewrite this exactly like this. We can actually see that this is a smooth variant of the filter I had before. Why? Because the weight vector I had here is the original weight vector I had convolved with this filter over here, which is a binomial filter, or box filter, same as a binomial filter of size 1. So this is simply a smoothed variant of this filter. It's equivalent to first do a smoothing and then compute the convolve it with this filter. Yes, please.
The underlined figure that represents the pixel which I'm calculating
yes.
on right now. So with the second data, shouldn't be then the first figure, the upper one, be the underlined one? Because the lower -1 is the pixel before. We said we will want to subtract the pixel before.
Okay, let's check. So function f, 1, 2, 4, for example. We are here in this location. Okay, we said this guy, so this is the value of 0, so this is the value of -1. Right? This is 0, this is the value of -1, index of -1. So this has the value of -1, and then this is the index 0 and index 1, -1, sorry, so it's there. Right? Because it's kind of exactly swapped. So this would be, if this is my coordinate I, this is my coordinate I plus 1, this would be f of I plus 1 minus f of I, my g of I. Right?
If you draw it like that, yes.
But that's the way I have to draw it. Because, so, the drawing I had before, well, this was f, this was I minus 1, I plus 1, and the other one had to be swapped. So this index -0, -1, and 1. And I have it like this. Then this is the index 0, which is -1, the index -1, which is 0, so that should be correct. So from my point of view, that's correct. Where is your misunderstanding? So if this is the index 0, this is the index -1. If I write it like this, maybe this is the confusion. So in here, for this one correspondingly, this would be the index 0, this is the index 1, and this is the index -1. Okay? Okay. So given that the difference in f, in the f values, can be computed by the convolution of this kernel with my function f, the first derivative is written by the difference in f divided by the difference of x. So I can see that as this function divided by x, which is a constant, so it's a scalar multiplication, convolved with f. Okay, so these are two functions. This is this function I had in here. They're divided by a constant, which is just the spacing of my pixels. And I convolve it as f, and this gives me the first derivative of the function, the intensity values. So if I now look to my kernel, go back one, so this kernel over here, same also this kernel over here, the sum of the kernel values of the weights, the coefficients are 0. They all sum up to 0. Plus and minus 1 and 0. Okay, so they all sum up to 0. Yeah, so the vector contains positive and negative values, and in sum they end up giving the result of 1. And if I now have a constant signal, so a constant intensity value, I basically always subtract one intensity value minus the other intensity value, so this gives me a 0 line. Because if I have just a constant intensity value, the first derivative is 0. So at least intuitively this makes sense. Right? So if I have a constant function, the first derivative is simply 0. This is something which matches with this one over here. If I have a slope which is constantly increasing of intensity values and compute the first derivative, I will simply get constant values everywhere, which is true because if I have a linear function, the first derivative is a constant, which is the slope of this linear function. Okay, I can even show this as an example. So I've this is the function I'm taking into account, and I used compute the first derivative of this function. So it's again smoothed over 2 pixels. So those values are in the order of 0. Then I have the big increase over here. Over here, the values are again close to 0 because it's more or less a straight line. And then I have a negative gradient where the function drops down, and then again a high gradient going up and down again. So at least intuitively, this seems to work quite well, giving me the first derivative. So far, we have done that only in the 1D case. But nothing prevents us from computing the derivative also in multiple dimensions. What we do now is simply, okay, we simply want to compute the derivative, the vector of derivatives consisting of the individual partial derivatives. We can use exactly the same what we had before. So the kernel function I defined just now in x and in y. So one is horizontal and the other one is vertical. Horizontal and vertical, right? Therefore, we have this index x and y in here. And then divided by the different size of the pixel. So for this function, can express this as this operator by convolving any function g. G is now here for gradient in the image. I get, with this operation, the gradient in x and the gradient in y. So performing this operation can do this once, computing for the overall image the first element, and then for the overall image the second element. So we're actually obtaining, you can see this as obtaining 2 images, where one are the derivatives with respect to the x direction, the other one are the derivatives with respect to the y dimension. Right? So this can be seen as one image, this can be seen as one image. So one image and one. So you can see there's 2 stacked images, this matrix, because one image, the first one, is the first derivative with respect to the x. The second one is the first derivative with respect to y. If I compute this for the image, I will get one derivative with respect to x and one derivative with respect to y. So I get actually 2 values per pixel. So I can see this actually has 2 images. One image gives me the gradient in x, and one image gives me the gradient in y. Okay? Okay, what can I do with that now? So again, I can say I have 2 images, the x and y. What I now can do is I compute the magnitude of the gradient by simply saying, okay, what is the gradient in x? What is the gradient in y? And compute with Pythagoras the magnitude of my gradient. What I can also do, exactly using the same thing with the Aton function, so if you use it in MATLAB with Aton 2, I can now compute the direction of the gradient by taking into account how much difference in x and how much difference in y. What's the gradient in x, what's the gradient in y? And this actually tells me the direction of the gradient. So I can now express this again as 2 images. So this is exactly what we had before. So what I basically do here, I do 2 convolutions. The image G is convolved with this one and with this one. This gives me my 2 images. And now I combine that by squaring those values, the 2 values per pixel, squaring them, adding them up and computing the square root, which gives me the magnitude of the gradient and then the direction of the gradient. I can express this with sine and cosine, or I could even take the angle. If I do that now, I can actually compute this for an image. Here's an example. So I start with this one over here. This is the original image that I have. I can then compute the changes with respect to y, compute the gradient in y, the gradient with respect to x. And if I then compute the magnitude of this gradient, I exactly get this image. What I can actually see in here, that actually fits quite well to all those areas where I have a steep gradient. So the areas with a low gradient, like this one over here, so there's more or less the grayish area. And here, add those edges, I actually have a very large gradient because I have a very strong change from bright to dark values. And I can even visualize the direction by just every color being a different direction of the gradient. I can actually identify if this is a gradient from bright pixels to dark pixels or from dark pixels to bright pixels, depending on this direction. So this is why this fancy color comes from. Basically, every color stands for an own direction. Okay, so at that point, I more or less done. The only thing I want to show is how we can actually then do that now in 2 dimensions. And so this is one of those operators, the so-called Wrobl operator, which is basically computes here, consists of the gradient we have in, or it basically consists of a convolution of a smoothing function. So B2 was the 1-to-1 kernel, and the gradient kernel is kind of again a smoothing of the gradient, and this gives me this kernel function over here in X. So folding a 2D image with this kernel now gives me the gradients in X. I can do correspondingly the same with Y. So I can do this the same with Y. Then I have my the kernel with respect to I, and then take the smoothing kernel the other way around. I obtain the Wrobl operator for the other direction, and which would be this one. And not surprisingly, this one corresponds to this. So this vector corresponds to this vector, this one to this one, and this vector to this vector, right? Because it's just a 90 degree, intuitively it's a 90-degree rotation of the image to compute the one in X and Y. And this is one of those kernels that we use in order to compute the gradients in an image. I have a few more slides, but I think we're going to do that the rest next week. No, the week after next week, because next week you have the Städtebau, and then make a short repetition of these gradient kernels and showing what we can actually do with those kernels. Thank you very much, and have a nice next week, and we see each other then in kind of 10 days or 12 days. Thank you.